Okay, so we can hear you and see your screen, so that's great.
Okay, great. Thanks. I cannot see you now that I'm in the presenter mode over here, but let me know if anything goes wrong.
Thank you for attending 2023 CICC Education Session 2 entitled Emerging Devices and Systems for Storage and Computing. I am Joseph Park from Apple Corporation, co-session chair with Professor Gerald Yu from National University of Singapore. In this afternoon session, we have two distinguished speakers. The first speaker is Professor Onur Mutlu from ETH Zurich, and the second speaker is Professor Spriyo Datta from Purdue University. Professor Onur Mutlu talk starts from the shortcoming of modern computing architecture in dealing with data, and then he will talk about data-centric, data-driven, and data-aware computing architecture that handles data well for efficiency and high-performance computing system. In his presentation, many related publications and articles are introduced as an example. So Professor Onur Mutlu obtained his PhD degree from University of Texas at Austin and is currently a professor at ETH Zurich. Prior to joining ETH Zurich, he was with Microsoft Research, Intel, AMD, VMware, and Google. Let's welcome the speaker. I think you can start your presentation.
Okay, thank you. Thank you very much, Young-Sok, for the kind introduction. And apologies for not being there. I wish I could make it there, but as you can probably hear from my speech, I'm a bit under the weather and I couldn't, I was advised not to travel. So I'm going to talk about memory-centric computing, as mentioned. I'm going to give a more of an architectural perspective. We're going to touch some circuit level aspects, some application level aspects, and some architecture level aspects as well. This is an area that we've been working on for quite some time, and I'm quite excited about it. And I will have a lot of slides. I think you have all of these slides in your CICC packet, but I will not cover all of the slides in great amount of detail. I'll provide a lot of motivation as to why we need to move to a more memory-centric paradigm today, especially at the beginning of the talk. And then we will look at two different kinds of memory-centric or data-centric computing design, processing using memory and processing near memory. And then we're going to talk about some adoption issues at the end. Okay, let's get started. I think if there are questions, you can feel free to interrupt if there's a burning question. I assume someone will handle the questions, but we will also have time at the end for questions. Okay, so today computing is bottlenecked by data. All important workloads that we have are data intensive, and these workloads require rapid and efficient processing of large amounts of data. On top of this, the data is increasing. We can generate more data than we can process in many, many domains. Now, this enables a lot of interesting opportunities for new applications, but this strains our computing systems significantly, as I will show you in the next several slides. And we want to do actually even more sophisticated things on the larger amounts of data, ever-growing amounts of data, and this is going to strain our computing systems even more going into the future. Clearly, one application domain that's very interesting to everyone today is neural networks, and everyone is interested in the large language models that are increasingly compute as well as data intensive today. And this is an example of the memory and compute requirements of neural networks growing exponentially over recent years. And unfortunately, our computing infrastructure is being dwarfed in this growth of neural networks. But it's not just neural networks. There are other applications out there that are straining our computing systems, databases, graph processing, data analytics engines, data-centric workloads. These are all data intensive, and they're straining our computing systems. They're causing performance and energy bottlenecks. Memory and storage system is increasingly a performance and energy bottleneck, as we will see in this talk in these applications. On the mobile end, there are other applications that are also quite data intensive today. As you can see some examples over here. We're going to cover these a little bit more later into the talk. And we're having performance and energy issues in these systems and applications as well. I will talk a little bit about genomics. This is an area where we're doing a lot of work. And I think this is another application where actually the data growth is really immense, especially even compared to other applications that we're seeing. And you can see that this is really fueled by the growth of high throughput sequencing technologies. These are devices and circuits at the core that can sequence a genome much faster and with much higher throughput and with lower cost than before. You can see that that cost has been reducing exponentially with the introduction of new sequencing technologies, essentially new devices. And you can see that the cost of a transistor as dictated by Moore's law, is reducing at a much lower rate than the cost of sequencing a genome. Now, this clearly indicates that we can sequence a lot more genomes, but our general purpose computing infrastructure that's built on transistor is not going to be able to keep up. In fact, it's already not keeping up. We have sequencing machines that are very, very powerful. In the end, we want to achieve scientific discovery and medical advancements. Unfortunately, we're bottlenecked by how fast we can analyze the data. And data is, again, a huge performance energy bottleneck in these applications. And clearly, genome analysis, we need faster and scalable genome analysis, as COVID-19 pandemic has proved. But there are many, many other reasons why we want faster and scalable genome analysis. I don't have time to go over these in this talk, but I'll point you to some papers that we have written. And you can see this is one of the technologies, nanopore sequencing technology. It's a very powerful device that can actually portably sequence genomes. But unfortunately, it's a great data generator, genomic data generator. But unfortunately, it's a terrible data analyzer. So it has zero computational power inside it. You have to move the data somewhere else to do the analysis to a laptop. But usually a laptop is very insufficient depending on the analysis that you want to do. And sometimes we move the data all over the world across data centers to actually do the analysis. Basically, can we do better? Can we actually do the data analysis much better in these data generation devices and move the data analysis much closer to the data generation devices? That's one of the things that we're examining today. But let me pull back and give you the bigger picture. So these are on the left, you see a special purpose machine for data generation. In this case, it happens to be a genome sequencing machine. This is a very powerful one. These are very fast, very special purpose. But in the end, we move the huge amounts of data that come out of these machines and move them to general purpose machines for data analysis, which are quite slow. Essentially, we have slow and inefficient processing capability and large amounts of data moved. Due to this fundamental mismatch between the specialization level of the machines and also the where we do the analysis. And the picture is very similar for many data generators and analyzers today. You can actually replace this genome sequence analysis machine with a video camera. Video camera is very similar, in my opinion, in terms of its data generation capability. It's very fast, it's special purpose. And usually we feed it to relatively slow general purpose machines for analysis, especially in the data centers. And you can actually replace this with other data generators like clicks on the web, etc. So basically, this picture is very similar today. And we would like to reduce the amount of data movement that we do by specializing the machine, the data analysis, and moving it closer to the machines as much as possible. And if you're interested in genome analysis, this is actually fascinating. I'm going to talk about that later on also. But there's a lot of specialization that we can do all the way from circuit levels, from the analog computation levels, actually, to the application levels and doing algorithm architecture co-designs. And these are some examples that you can read if you're interested to get into the field. Because it's not an easy field to get in. Genome analysis has a lot of jargon and terminology. But in the end, it's an important area, in my opinion. It encompasses neural networks also, because there's a lot of neural network-based analysis that you do within the scope of genome analysis. And if you're interested, you can take a look at some of these papers. I will mention what you can do today with today's hardware, accelerating some of these applications. So we did this work together with IBM a couple of years ago. What we did was basically we took the FPGA boards that are capable of accessing memory with high bandwidth and that can we can reconfigure to customize for the application. And this FPGA board has high bandwidth memory. And we basically offloaded carefully some portions of the genome analysis application, as well as a weather modeling application called Cosmo, to accelerate these applications such that you can utilize very high bandwidth memory access. You can consider this as an example near memory acceleration you can do today using real systems. And we use the OCAPI interface, which is actually kind of similar to the CXL interface that's being developed or that's being used more widespread manner in the industry today. Essentially, by doing so, you can gain significant performance energy improvements. I'm going to refer you to the paper for more details on how we do that. But on a genome analysis application, for example, performance improves by more than 1 order of magnitude compared to a general purpose CPU. A powerful general purpose CPU, and energy efficiency also improves by more than 2 orders of magnitude, again, compared to the same CPU. And you can do even better by more algorithm architecture co-design. I'm not going to talk about some of these works, but I'll refer you to them. I'm going to talk about in-storage processing that actually reduces the data movement even further by doing the computation inside the storage device. And you can there are actually other applications that we need to look into in this domain, like sequence to graph mapping, because graph analytics is becoming even more important, even in genome analysis. And then you can combine different parts of the genome analysis pipeline to actually reduce data movement as much as possible. This is a work where we used non-volatile memory technologies to accelerate again base calling and mean mapping together on the same chip, if you will. And there's more to talk about over here, but we don't have time. But you can see that there is actually a lot to do in this domain of genome sequencing and analysis by customizing the circuits nicely to the algorithms and designing the algorithms together with the circuits. And if you're interested, again, there's a lot more talks on this. I'll let you take a look at it if you're interested. So this was an example application. I believe actually if we do the right things in designing our circuits and algorithms together and architectures together, we can come up with emerging devices, in fact, to enable genome sequencing in a much better way. But where are we today? Today, unfortunately, we're not there. Today, these applications are overwhelming our modern machines. They're overwhelming the storage and memory capability, the communication capability, and in the end, the computation capability. And we have actually very powerful compute devices today. We're going to talk about that. Unfortunately, most of the time, these compute devices are waiting, doing nothing but waiting for data. And also, data is greatly impacting robustness, energy, performance, and cost. And we're going to talk about that from the context of technology scaling first. If you look at the fundamentals of a computing system, you need three key components: computing, communication, storage, and memory. Today's systems are very, very compute-centric. Before we can actually do anything on the data, we have to bring the data to the computing units. Today's computing units are very heterogeneous. It could be CPUs, GPUs, FPGAs, machine learning accelerators, or different types of accelerators like video accelerators. But unfortunately, they're all compute-centric. We cannot process data in the memory and storage units or the communication units or anywhere else other than the computing unit today, basically. Let's take a look at this computing units. Basically, we have a very processor-centric design today. If you look at the computing unit, this is a general purpose picture, if you will. You process data inside the cores, but everything else other than the cores is dedicated to storing data, moving data, basically caches, interconnects, other caches, other interconnects, memory controllers, other interconnects, other caches or main memory, other interconnects, and storage device and other interconnects. Basically, if you look at a single node, more than 95% of the real estate of a node is dedicated to storing and moving data. Yet we call these computing devices today, compute chips, if you will. Yet, unfortunately, the system is still bottlenecked by memory. So maybe we're not doing something right in our systems because we're dedicating almost all of our resources to memory and communication, yet we're still bottlenecked by memory and communication. And if you don't like my picture, this is a picture from AMD. You can see the area dedicated to L2 and L3 caches, not all of memory. You can see that that's most of the chip, and there's a global memory interconnect over here. And we're adding more with 3D stacking. This is actually beautiful 3D stacking, but we're adding more and more caches. Is this the right thing to do? And that's not so that we don't single out AMD. There's IEDM, but essentially the industry is adding more and more caches, many levels of cache hierarchies, essentially. And this is a picture from Apple, which is used in a lot of mobile chips today, clearly. I think of the compute chip as a lot of SRAM. The bottleneck over here is a lot of DRAM. And then there's a darkness over here, which we don't normally consider, which is storage. So all of these places store data. Why are we doing processing inside the computing chip today only? Okay, so I think you kind of know where I'm getting at, but I'm going to motivate this a little bit more. If you look at the applications that we use today, these are mobile applications. We did this study with Google about 5 years ago, actually, right now. And on these workloads, we found out that more than 60% of the total system energy is spent on data movement. And these workloads actually fit in main memory. And these are not the most data-intensive cases. We did some other studies together with Google also, where we analyzed their edge machine learning workloads, machine learning models. I'm going to talk about this a little bit more later on, where we found out that more than 90% of the total system energy is spent on memory in especially difficult machine learning models like LSTMs and transducers. So increasingly, we're going to be more memory bound as the applications grow. And again, we're not talking about storage over here. We're talking about applications that fit memory. Once you actually don't fit memory, once you have terabytes and terabytes and terabytes of working sets, you're actually bottlenecked by storage. Okay, my axiom going forward in this lecture will be that an intelligent architecture needs to handle data well. And we do want intelligent architectures because these are going to be making decisions for us, whether or not we like it. They're already making decisions for us. So the question is, how do we handle data well in our systems? I think there are three major directions. In this lecture, we're going to focus on especially the first one. I'm going to give you a flavor of the other two before we move on to the first one. First, I believe we need to design systems that doesn't get overwhelmed with data movement or data. For this, we need to have intelligent algorithms, architectures, and system designs. We're going to talk a lot about this. Second, I think we need to have the systems that can actually take advantage of the vast amounts of data and metadata flowing through the system so that we can keep improving our architectural and system level decisions. I call this data-driven systems. Essentially, we need to design our controllers to learn from experience and the data they see. Today, we design controllers that are human-based. Humans dictate the policies and heuristics. But why don't we have controllers that learn from what they see and over time improve their decisions? For example, the memory controller can be a reinforcement learning agent that can improve its decisions based on interaction with the environment, as well as the workloads, as well as the system, as well as the user. That could be true for the cache. That could be true for the storage controller. That could be true for anything that we design, essentially. The third, and this is synergistic actually with more data-centric systems that I'm going to advocate more in this talk. The third thing to do, I believe, is to handle data well, is to really understand and exploit properties of different data. We have a lot of data that's flowing through our systems, but a lot of its characteristics are either unknown, undiscovered, and even if it's discovered, it's not communicated to the underlying hardware. But if we communicate this information to the underlying hardware, we can improve our algorithms and architectures and maybe even circuit designs in various metrics. I'll give you some examples. Data has a lot of properties. Data has approximability properties, error tolerance properties, compressibility properties, locality properties like performance properties, criticality properties in terms of performance, and criticality properties in terms of security and privacy. For example, if we know that a piece of data is a lot more security critical than some other piece of data, maybe that information needs to get communicated to the memory controller such that that piece of data is handled extremely carefully by the memory controller, such that we don't open up side channels when we access that data. Today, that information doesn't get discovered or even communicated. Today, the memory controller essentially treats all pieces of data the same. So, okay, I think I've kind of given you the idea of the data-driven and data-aware systems. Today's systems make designer-dictated decisions as opposed to data-driven decisions, and they make component-based myopic decisions as opposed to data-aware decisions. And we need to enable that type of decision-making. But in today's lecture, we're going to talk about moving from processor-centric systems to more data-centric systems. But please keep in mind that I believe these three directions are very synergistic. A data-driven system can benefit from a data-centric system, and a data-centric system can greatly benefit from being data-aware, meaning understanding the different properties of data going into the future. So that's why we advocate this data-centric, data-driven, data-aware computing paradigms. So if you look at this, I think to be able to really enable this sort of computing system, we need to revisit the entire stack of what we're doing with our computing devices, all the way from devices, circuits, logic, microarchitecture, ISAs, system software, languages, programs, and algorithms. And we need to co-design across the stack. But I believe we can also get there step by step. So it's not a hugely daunting task, even though the longer term solution is longer term. Shorter term, I believe we can actually have some advances that could be quite impactful. And I'll hopefully give you some examples of that. But if you're interested in the vision, I'd recommend you take a look at this short paper that we were invited to write for the DATE conference in 2021. Now, let's jump into the data-centric or memory-centric architectures part of this paradigm. Even if you look at a data-centric architecture, there are many properties that we would like to satisfy, in my opinion. First and foremost, we're going to talk about that a lot in this talk. Processing data, we need to process data where it resides, where it makes sense, where the data is generated. Today, we have no choice. We process the data in the processor. Why not have the choice so that we can process the data in the sensor structures, near memory, near storage, and everywhere? We're going to talk a lot about that. But I also believe that we need to enable much lower latency and lower energy data access. I don't think we're doing too well in this direction. And there's a lot to do, again, across the stack over here, especially in the circuit and device levels. We need to enable much lower cost data storage and processing. And again, there's a lot to do over here across the stack, hybrid memories, compression mechanisms, fundamentally denser storage architectures. And we also need to more intelligently manage our data so that we can be more robust, more secure, and lower cost and higher performance. So there's a lot over here. Again, I'm not going to focus on the last three, except I will motivate the processing data where it resides a little bit with the technology scaling problems that we're having. So we're going to touch upon those, but we're not going to focus on those. We're going to focus especially on this, processing data where it makes sense. And if you look at a mobile system that looks like this today, there are a lot of places where we can process data. We can process data when it's actually captured inside the sensors. We can process data while it's sitting in the storage. We can process data while it's sitting in DRAM. We can process data while it's sitting in caches, but we don't do any of those. We actually wait until we bring the data to the processor or an accelerator or whatever computing unit there is. Even the registers or the SRAM that's very close to the computing unit is incapable of doing processing on the data. So we're very processor-centric, basically. So we would like to change that. We would like to actually process data where it resides. And this is an old idea. This is not a new idea. This was proposed in the 1960s. Maybe there are earlier papers. If there are earlier papers, please let me know. This is the earliest paper I could find that clearly delineates the concept of processing in memory. They called it logic in memory, but essentially it's what I call processing near memory. Put the logic units next to the memory such that you don't move the data a lot. Their motivation was a little bit different. You can read the papers. And this is a concurrent paper by Harold Stone, which you may be familiar with from 1970. So what's different today? Basically, this idea has been examined for 60 years with some ons and offs, and people have looked at this idea in different perspectives. Why is it much more interesting today? Basically, I think today we don't have a lot of choices. We're kind of squeezed in the middle. Why? We're having huge problems with memory technologies that we have today. Technology scaling is not going well, especially in the main memory side, but also in the storage side. And these scaling issues demand more intelligence in memory. For example, the RowHammer problem I'm going to mention a little bit, but it's not just the RowHammer problem. It's a bunch of technology scaling issues that require intelligent controllers to make our memories more robust, secure, and also high performance at the same time. I'm going to talk about this. I'm also going to talk about the huge demand from application systems. So at the higher levels of the stack, we're having a lot of problems with our application systems. Data access to bottlenecks. We're having a lot of problems with energy and power. And data moment energy is dominating computation energy. And also our demands have increased. We need performance, energy, and sustainability all at the same time. And we don't have a lot of choice if we really want to improve all of these at the same time. By minimizing data moment, we can actually improve a lot of these. So we're kind of squeezed in the middle. Technology is demanding intelligence on the memory side, and applications are also, and the systems are also demanding intelligence on the memory side, and we're kind of squeezed in the middle. So that's why processing in memory is kind of investigated a lot more heavily today. So people have been investigating 3D stacked memories. You have a logic layer underneath memory layers, and you can do computation on the logic layer. Micron has been looking at automata processing, where you can actually do processing, limited processing inside the row buffer. And more recently, the UPMAM company in France have introduced general purpose processing units inside the DRAM chip. We're going to talk about that. Samsung has introduced, again, processing units specialized for machine learning inside the DRAM chip. SK Hynix did something very similar. Samsung and Meta, Facebook together introduced these modules where you can actually do processing near memory inside these modules. And more recently, Alibaba also introduced their DRAM chip that can actually do recommendation inference similarly to this, but in a different way by modifying the DRAM chip. So you can see that in Circuits Conference, a lot of these were actually published in IEEE or hot chips in the past. There's a lot of movement towards processing near memory, especially because of the reasons that I mentioned. And there are many, many other experimental chips and startups. ISSCC, CICC, as well as architecture conferences feature a lot of these that I do not depict here. I actually depicted the main commercial ones over here, but there are also startups that actually build processing near memory as well as processing using memory chips that we're going to discuss. So let's talk about this technology scaling aspect first. Why is technology scaling not going well? Basically, we're kind of reaching the limits, especially of DRAM scaling. And as a result, industry is open to examining controllers close to DRAM. And industry is also open to new memory architectures, especially emerging technologies, but also new ways of using DRAM or putting value into DRAM. That's why we're seeing these techniques, in my opinion. But let's talk about the technology scaling aspect first. So technology scaling has not been going well for a while. We've kind of been tolerating it in different ways. In this IMW International Memory Workshop paper and invited talk, we argued that we should really take a systems architecture perspective because we're going to have a lot of device and circuit level scaling issues. We can actually optimize the stack on the memory such that memory can become much better over time. And over time, we collected a lot of data. I'll give you some example reliability issues. This is some data that we collected together with Facebook over the course of multiple years. We basically analyzed all of the memory errors that they see in all of their data center servers. This is production data centers. And we can do a correlational study. And we basically looked at the correlation between the DRAM chip density employed in the server and the relative server failure rate that we observed in the field. And you can see that there's a strong correlation. If you really want to understand the metrics, you got to read the paper. But basically, the takeaway is that as DRAM chip that gets employed in the data center server gets denser, you get more errors and more failures at the system level. Why? Because the cells of the DRAM chip are smaller and closer to each other. As a result, they're more vulnerable to noise, and they have a lot more reliability issues. And this gets exposed to the higher levels as memory errors and application failures as well in some cases. So we also wanted to study these effects at the smaller scale. So we built a lot of FPGA-based infrastructures to test DRAM chips. And we did a lot of testing. You can read our papers if you're interested. These are some infrastructures more recent infrastructures, and we have very fine-grained control over timing, temperature, and voltage with these infrastructures. So while we were doing these studies, some of the studies that we did together with Intel, we showed that you can predictably induce errors in most DRAM memory chips. And this is known as the RowHammer problem. Some of you may be familiar with it. But basically, the problem is, this is something that should not happen. You're accessing memory, and accessing memory introduces errors. And this should clearly not happen, right? Because you should not change anything. We're not even writing to memory, actually. Nothing should change in memory. Let me give you the basic idea. The basic idea is memory consists of rows of cells, a bunch of different rows. If you want to read some cell in some particular row, you need to apply high voltage to the word line that is associated with that row. This is called an activate command in DRAM. Now, if you want to read some other cell, you apply low voltage. You close the word line, basically, to that row. Now, if you keep doing this repeatedly, high voltage, low voltage, activate, precharge, activate, precharge, activate, precharge, activate, precharge, enough times before the cells get refreshed in DRAM, it turns out you get bit flips in physically adjacent rows. Clearly, this is a read disturbance mechanism. Whenever you're reading a row, you're disturbing cells in other rows. But this is happening in the chips in the field in real DRAM. So we call this the hammer row. We call this the victim rows. And we showed that more than 80% of the chips that were manufactured by 3 major DRAM manufacturers were vulnerable to this effect. This is 2012. Today, all chips are vulnerable at the device and circuit level, basically. All of our tests show that. I'm not going to go over that, but I'm going to refer you to some papers. So this is a technology scaling problem because cells are much smaller today and much closer to each other. So this disturbance mechanism gets exposed to the user because you could do enough activates within a refresh interval that causes these bit flips. In the past, you couldn't do that, basically. And unfortunately, this is not just a reliability or robustness or safety problem. It's also a system security vulnerability because someone can take advantage of those bit flips to take over your system or leak private data. And you can read articles, even popular articles like this that talk about that. I like this one because it says, forget software. Now hackers are exploiting physics. And that's kind of a nice description at a high level of what RowHammer is. Okay, I'm not going to talk a lot about RowHammer, but you can find a lot more information. Actually, we gave a tutorial at the International Memory Workshop on this topic last year. And you can also find other information as well. You can read our papers and other papers too. This is a retrospective that was written in 2019, but we updated more recently because RowHammer is still going on. And I think we need some solutions to it. So one solution is making the memory controller a lot more intelligent, or making the DRAM chip a lot more intelligent such that it can detect these access patterns. It can protect against them. And this is already happening, both at the memory controller level as well as the DRAM chip level. I'm going to talk about that briefly, but this is essentially what I'm talking about. We need these intelligent memory controllers to overcome some of these technology scaling issues. And this intelligence needs to increase going into the future because there are other issues that we're going to have with memory at the circuit and device levels going into the future. So other issues, let's say RowHammer is one issue, but DRAM has a lot of other scaling issues. And maybe a good idea is actually not to rely on DRAM as the main memory technology going into the future as much, but augment it with some other memory technology as well. This could be phase change memory, STT-MRAM, RRAM, memristors, your favorite memory technology. Now, the good thing of this, or it could be some other type of DRAM as well. The good thing of the solution is now you have a hybrid memory system, and it has different kind of characteristics in the different memories. And hardware and the software can manage the data allocation and movement between these different memory technologies such that it achieves the greens of each memory technology as much as possible, while avoiding the reds or downsides of each memory technology as much as possible. Now, this has been an area that has received a lot of investigation, scientific investigation, and also there are systems that have this sort of memory today. But basically, if you want to do this, you really need an intelligent controller as well. The controller needs to understand the characteristics of the device, as well as the characteristics of the application, so they can match those things to each other. So I think the takeaway is clear. We need intelligent memory controllers, and this is already happening. This is an example of solution to RowHammer. We've actually been designing these intelligent memory controllers to fix the RowHammer problem and other scaling issues. If you're interested, this is one example that Intel found worthwhile to award it as a finalist in the hardware security contest that they have. And I should also mention that industry is writing about the papers about it. This is a paper from Samsung and Intel in 2014. While we were talking about RowHammer, they were actually saying that we're having difficulty in DRAM process scaling challenges. And they talk about a bunch of scaling challenges, which I agree with. There are actually a lot of interesting scaling challenges. And they basically said that it's difficult to overcome these challenges at the device and circuit level solely. So we should really co-architect architectural controllers as well as the DRAM devices together, such that the controller can solve these problems more easily. And we see that happening. This is IEEE this year, a couple of months ago. SK Hynix wrote the first paper that publicly acknowledges the RowHammer problem by a major DRAM manufacturer. And they actually talk about some solutions, some of which are variants of what we have proposed. If you're interested, you can take a look at the paper. This is the abstract of the paper. So it's really good that I think industry is actually finally writing papers about RowHammer. But what they're doing is they're putting intelligence inside the DRAM chips. So they're putting non-trivial logic inside the DRAM chips to keep track of frequently activated rows and refresh them as much as the DRAM standard currently permits. Okay, there's also other papers that are written by other industry. This is a paper by Samsung that was put on archive at a similar time as the IEEE CICC conference that also talks about some RowHammer solutions, some of which are actually variants of what we have proposed in the past as well. So with intelligent controllers, you can actually do other stuff. For example, in this work that we've shown that you can identify uncorrectable errors in memory chips. I will let you read the paper to figure out how it's done. But you can also say that these intelligent controllers are not new. And you would be right, because we've been designing very intelligent controllers to manage NAND flash memory for a long time. And these are NAND flash memories everywhere in our SSDs, clearly. We've actually hit a lot of technology scaling and reliability issues on NAND flash memory much earlier than in DRAM. As a result, we've been designing controllers that make the bits in flash memory work by adjusting the voltages intelligently, predicting a lot of different things like wear outs intelligently, and also doing a lot of management functions intelligently. So there's a lot of computation going on inside the NAND flash controller. I believe DRAM is going to be similar. So we've been also working on NAND flash memory for quite some time, and we've been writing papers. If you're interested, you can actually find out a lot more about this. The difference here is I think main memory is actually going to have similar controllers, but we need to be a lot more careful with main memory because the technology is much faster than the NAND flash technology. Okay, you may also say that there are emerging technologies. Maybe some emerging technologies will solve these technology scaling issues. As a result, we won't have intelligent memory controllers. I wish you were right. Unfortunately, these technologies have a lot of deficiencies as well. So in order to overcome some of these deficiencies, like endurance problems, some other reliability issues, we really need intelligent controls. And we've also been working in this area for some time, and we've been proposing some intelligent controllers to overcome some of the deficiencies of emerging memory technologies. So basically, I think my takeaway is that intelligent memory controllers are needed to avoid many failures and enable better technology scaling going into the future. And this is already happening today. Now let's take a look at the higher level of the stack. So we've looked at the circuit and device levels pushing us to have intelligence on the memory side. I think systems and applications are even worse, if you will. Why? Because we're having a lot of scalability problems. Basically, data access is a huge bottleneck. Energy consumption is a key limiter. And data moment energy dominates computation today. Before I go into quantifying some of these, I will also take a step back. I think we should really think about the future of our, let's say, world and universe, and also the role of computing in it. Today's computing systems actually consume a lot of power. They actually are responsible for a lot of carbon, but this is growing exponentially. This is going to become even worse. Data centers and billions of devices that are out there. Do we want a world that looks like this, or do we want a world that looks like this? I will argue that we would like a world that's energy efficient and sustainable, and our computing devices need to be that way also. But we also want high performance so that we can solve lots of the problems that we're dealing with. So we want everything at the same time. We're greedy. Unfortunately, we're not doing very well on the energy efficient and sustainable side, and also on the high performance side, I would say. Because data access is really the major performance energy bottleneck today. And our current design principles from the very fundamentals of computing cause great energy waste as well as great performance loss. I put this performance loss in parentheses because we recognize this. We recognize that whenever we move data from memory to a processor back and forth, this causes performance loss. This also causes energy waste, of course. But we try to do a lot to overcome this performance loss. We actually complicate our systems a lot. I showed you a lot of pictures that do this. Basically, most of our computing devices are dedicated to caches. Basically, most of our systems are caches. And that's actually to overcome the performance loss. And then we also add prefetchers. We also add heavy out-of-order execution mechanisms. And we also add heavy levels of multi-threading. That complicates our systems. And most of the time, these mechanisms actually don't work very well. When they work, that's great. But usually they don't work. Sometimes they help work. In many applications, they don't work very well. As a result, they compound the energy waste. So they add a lot more complexity and they compound the energy waste. In fact, we try to get rid of the caches when we try to access memory. For example, we wrote a paper at Micro last year. It got the best paper award. And the idea was to use machine learning to identify which loads are actually going to miss the cache hierarchy so that we can start the memory access much faster. We want to bypass the cache hierarchy when we're not going to hit in the cache hierarchy. And there are a lot of applications that don't hit in the cache hierarchy. So basically, we have a problem. We're compounding our energy waste by adding more complexity in our systems. So the main problem is the processing of data is performed far away from the data. We have no choice. We have to bring the data to the processor. So we're back to the picture that I showed you earlier. The computing unit is the king. All data is processed in the processor at great system cost and at great energy cost, at great performance cost. Yet we know that memory is a problem. So it's not something we don't know, but let's quantify this a little bit. So this is a paper that was written by Dick Seitz, who was the chief architect of alpha processors in the 1990s. After they designed the flagship alpha processor at the time, he basically wrote this article saying that it's the memory stupid. Basically, he said that we designed this processor. It's capable of finishing 4 instructions every clock cycle. Unfortunately, on this important database workload, which we thought we designed the processor for, it's finishing 1 instruction every 4.7 clock cycles. So it's operating at less than 5% of its peak bandwidth. Why? It's waiting for data to come back from memory. And he finishes the article saying that I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. Okay, fast forward about 10 years. This is data from my own PhD thesis. We analyzed the applications that Intel was using to design their processor with at the time. And we found out that most of the time, the same thing is happening. The processor is waiting for data. And if you're interested, you can read the first paper I ever wrote, if you. Now, fast forward about 10 years. This is Google showing all of their data center workloads according to them. And they basically show the same thing. On a flagship Intel processor at the time, most of the time, the processor is waiting for data on these important data center workloads that a lot of us are probably using even right now. And if you're interested, you can read the paper also. So basically, we have a grossly imbalanced system. Because processing is done in only one place, data moves a lot. This is energy inefficient, low performance, and complex. And we complicate our processor and accelerators even more to tolerate this data access. We have complex hierarchies and mechanisms. And this is also energy inefficient, low performance, and complex because we could have used all of that hardware to actually do processing, as opposed to trying to tolerate this huge data movement overhead, which we cannot easily tolerate. So that's why we have this picture that I showed you earlier. Most of the system is dedicated to storing and moving data, yet the system is still bottlenecked by memory. Okay, that was kind of the performance efficiency perspective, but let's take a look at the energy perspective in more detail. I think this was shown in an earlier talk as well, but I'm going to quantify it a little bit more, relying on some data points that was presented by Bill Daly, NVIDIA's chief scientist, some time ago. You can argue with the numbers, but you cannot argue with the, let's say, relative differences. So basically, we're wasting a lot of energy. Energy is even worse. Today, a complicated double precision floating point operation, according to this number, is 20 picojoules. A DRAM read or write access is 16 nanojoules. That's 800x difference. Okay, if you find 800x too large, it's closer to maybe 160 to 200x. Basically, a memory access today consumes between 2 to 3 orders of magnitude the energy of a complex addition operation. Now, does it really make sense to actually do 2 memory accesses to bring 2 operands from memory and then write back the data with one more memory access to main memory. Now you can say that we have caches, but do the calculation to actually overcome this energy differential. You really need to reuse the data thousands of times. And this is not going to get better. In fact, if you're doing a simple operation, the problem is even worse. A simple memory access, so a simple 32-bit arithmetic operation is much less energy costly. As a result, a memory access is much more power hungry or energy hungry comparatively. So to overcome this huge energy differential, you need to have really huge amounts of locality in your data. And in many cases, we don't have that amount of locality. Okay, so there are other papers you can read about this. These are in the slides. But that's why we actually see this huge amount of fraction of total system energy spent on data movement in real applications. Okay, so I will argue that we do not want to move data. We want to be minimalist in our data movement. We want to enable computation with minimal data movement. For this, we need a paradigm shift. We need to compute where it makes sense, where data is generated and where data resides and where data is moving, for example. And for this, we need to make computing architectures more data-centric. So in the rest of the talk, I'm going to talk about especially processing inside main memory. We're going to look at main memory that has databases, graphs, media, lots of programs basically inside the main memory. And we're going to be able to query it, ask questions to it. Memory, can you execute this operation for me? And the memory responds with the results. Now, this sounds nice. We should be able to do this for the storage. We should be able to do this for the sensors, etc. And you can see that this is still an accelerator type of model. I think going forward, we really need to take even a further step where these components, memory, storage, sensors, are even more intelligent. And they don't need to be accelerators, if you will. They could be directly programmable. They don't need to serve the processor going into the future. But we're going to treat this as an accelerator so that we don't destroy the programmability aspects. Even with this accelerator model, there are many questions. How do you design the compute-capable memory and controllers? How do you design the processors and communication units? How do you design the software and hardware interfaces to enable this sort of processing in memory? How do you design the system software compilers and languages to take advantage of this and to make it easy for the programmers? And how do you design the algorithms to fit the devices and the circuits that are doing the processing? And also rethink the theoretical foundations of computing. You can see that these questions are all across the stack, and some of them require communications across the stack. I will mention one thing related to theoretical foundations and algorithms. Algorithms, I think, need to be redesigned so that you can really take advantage of the processing capability at the device level and the circuit level. But theoretical foundations is some place where we don't have a lot of knowledge today. If you look at how theory of computing has evolved, it's very processor-centric. For example, in a theory of computation course, you learn about the big O notation. That's algorithmic complexity. We basically count operations, count computation operations. But we just discussed that computation operations are not that important. Maybe we should really be counting data movements. So we really need a data-centric theory of computation to back up processing inside memory that we're going to discuss. Okay, so we actually have a paper that we keep updating online on arXiv. If you're interested, we cover a lot of these topics and even more. I don't have time to cover everything that's covered in this paper, but I'm going to focus on some things. We're going to define two different types of processing in memory, and then we're going to talk about adoption issues, and then I'm going to give you some examples from the real world that's happening right now. But I will also invite you to the processing in memory course that we've been holding. This is all on YouTube, live streamed. If you're interested, you can actually join this course and provide any input or just learn. But I will also mention that we need to think differently from the past approaches. Past approaches to processing in memory, we're not thinking adoption issues as much. I think today we need to really think about the adoption issues. So we're going to get back to that. But let me first define the two different types of processing in memory. I think there are only two different types of processing in memory. I call these processing using memory and processing near memory. These are fundamentally different. I'm going to illustrate them with my hands, if you will. This is the processor today. This is memory. Let's talk about the processing near memory first. Processing near memory says, put the processor or logic closer and closer and closer and closer and closer, such that at some point it's integrated with the memory chip. It could be inside the subarrays. It could be next to the bank. It could be inside the memory controller. It could be in a logic layer in a 3D stack logic. But basically, you have distinct logic and distinct memory, and they're coupled together. So this is, you get closer and closer to memory. So if you think about this, this is relatively similar to today's architectures. The logic is very similar to von Neumann architectures. It could be an accelerator also. So this is more easily programmable. And this is easier to do in the shorter term. That's why I'm not going to talk about it first, at least. I'm going to talk about the second aspect, processing using memory first, which I believe is longer term. But here you have processor and memory. We forget about the processor. We have just the memory. We designed this as memory today, but all memory has some computation capability or operational characteristics that enable it to do computation as well. These are analog operational characteristics that we can discover to make it to do computation. And I'm going to talk about that. I believe all types of memory is capable of this, sometimes with adding minimal amount of logic, sure. But we should really think about the memory device as a compute device as well. And from the very device and circuit levels. And I think this is probably the right conference to really talk about this. I believe this can be done. And there are many examples, and we're going to talk about some of those examples, especially focusing on DRAM, a technology that many people think it's commodity, but actually you can do analog computation inside the DRAM chips, as I will discuss soon. So basically, that's the idea. So we're going to start with that one. Processing using memory is the idea of taking advantage of operational principles of memory chips or memory devices or memory circuits to perform bulk data movement and computation inside the memory. What can we do? We can exploit internal connectivity to move data. We can exploit analog computation capability, and we can also add more, basically. We can do more. So before I go into this, actually, I should say that these two are complementary. These can be combined together. And if you really want to take advantage of processing in memory, I believe you really need to combine these together. Because processing using memory, in my opinion, is not enough. You need to really add some logic to do more complicated operations. So you will need both in the end. Okay, so I'm going to give you some examples of processing using memory. And I'm going to cheat first. I'm not even going to talk about computation. I'm going to talk about data movement or data copy and initialization. And this is important. We actually do a lot of data movement in our systems or data initialization. Imagine that you're initializing a 10 terabyte database. You actually write zeros or some random number to all of your memory. And this takes time. This takes energy. What do we do today? Today, we go through the CPU. I'm going to talk about that. Because of that, Google has shown that in their data center workloads, all of their data center workloads average out approximately 5% of the execution cycles is spent on two function calls, only two function calls, memmove and memcopy. I think this is fascinating. So there's a lot of data movement that we do in our systems, as you can see, and there are many applications over here. So how do we do data movement today? If you want to copy a source page, let's say 4 kilobyte to another destination page, today you have to go through the processor. You have to go through the CPU, at least through the memory controller, through the direct memory access engine. Because we're processor-centric, memory cannot do things on its own. So that's the idea, basically. Going into the future, we should not really go through the CPU. We should tell memory, please copy this page to this other page, or please initialize this page to zeros for me. That's the idea of row clone. And this is low latency, because we're going to exploit the internal connectivity inside the memory chips. This is low bandwidth utilization on perhaps one of the most important system resources, the memory bus. This is, you cause no cache pollution, but you could eliminate that today by going through the memory controller. And no unwanted data movement on, again, one of the most important resources, the memory bus. I'm going to show you a mechanism that takes a 4 kilobyte page copy from 1,000 nanoseconds today to about 90 nanoseconds, unoptimized, and then 3.6 microjoules to 0.04 microjoules. And the idea is very simple. In the best case, the source and destination pages are in the same DRAM subarray in DRAM. We're talking about DRAM. And if you look at the DRAM subarray, it's a bunch of rows connected to a row buffer, essentially sense amplifiers, bitline sense amplifiers. The idea is to first activate the source row, which brings the data into the row buffer, and then activate the destination row, which deactivates the source row implicitly and connects the destination row to the row buffer. By basically using the row buffer as an intermediate place to copy data, we copy data from the source row to the destination row with minimal latency. If you can do this faster in DRAM, you have to modify the DRAM significantly. But here, you could do only 2 consecutive activates and negligible hardware cost. If you want to do this reliably. If you don't want to do this reliably, you can actually do this in existing DRAM chips. You violate the timing parameters. If you violate the back-to-back activations that you do to the same subarray, you can actually get this row copy in real DRAM chips. I'm going to talk about that briefly, but I've already told you. So this actually increases your reduces your latency of 4 kilobyte page copy by more than an order of magnitude and memory energy by 74x, according to our calculations. It has significant impact on real applications, and you can read the paper for more detail. And later works actually showed that this is true, and later works build on this. This is one later work. This work showed that you can actually perform these row clone operations by violating the DRAM timing parameters using the soft-MC infrastructure that I showed you, the FPGA-based memory testing infrastructure that we developed. You need to carefully do this, of course, but if you do this, you can reliably get this copy in existing DRAM chips. These are DRAM chips that are designed not to do this. I mean, that are not designed to do this explicitly. We're violating the timing parameters. Basically, we're showing that you can actually do this in real DRAM chips. Now, imagine what you can do if you actually design the DRAM chip to do this reliably and to do other things reliably. We're going to talk about those other things. Now, we built on this work. We actually have an FPGA-based infrastructure that anyone can use, where you can actually replicate this violation of timing parameters to mimic data copy. We can also generate true random numbers in DRAM. So you can actually do a random function call inside your program that gets translated into commands in the FPGA that violates the timing parameters to get you random numbers out of the DRAM chip. I'm going to briefly talk about that, but you can also read the paper. That's another example of processing using memory. And this is real. You can download it. We're happy to support it if you're interested. And you can take a look at the results also that you get at the system level. So at the system level, you can get significant throughput improvements because we actually redesigned the operating system slightly to make sure this works well. So there's a lot more to talk about over here, but I don't have time. You can actually watch lectures, etc. But now you can see the mindset. We're actually designing the memory as an accelerator. In this particular case, we're accelerating copy and initialization operations that the memory is already very good at. We're adding slightly specialized compute capability, a data moment initialization capability in this particular case. And none of the other accelerators are capable of doing that because they're sitting on the left side of the memory bus, which is the wrong side, whereas memory is much better at doing this because it's not moving the data that much off the memory bus, which is the heavy power-hungry interconnect. So memory is similar to a conventional accelerator, except the data moment is much lower in this particular case. Okay, so I kind of said I cheated, but let's talk about computation. So in DRAM, similarly, we can support bitwise AND, bitwise OR, bitwise majority, and bitwise NOT at low cost using analog computation capability of DRAM. And the idea is to activate multiple rows, and activating multiple rows actually performs computation. And we see significant performance energy improvements in these bulk bitwise operations. And if you actually design your algorithm to take advantage of it, you see significant end-to-end performance improvements, energy improvements as well. And you can take a look at this paper that talks about this. Before I move on, I should mention that new memory technologies enable even more opportunities. There's a lot of new memory technologies that are coming up. They actually enable operation of data with minimal data movement because in DRAM, reads are destructive, and you don't have that problem in these emerging memory technologies. I'm going to talk about emerging memory technologies briefly, but I know that another educational session talk focused on that, so I'm not going to talk a whole lot about that. I'm going to talk to you about non-emerging memory technologies that everybody is using today, if you will. Okay, so let's take a look at how this is done in DRAM. This is, now imagine 3 rows, A, B, C. I'm showing you only 1 bit in each row, 3 word lines, and 1 bit line. And I'm showing you the bit line sense amplifier that's connected to the bit line, essentially. Now imagine that this row is 8 kilobytes. So you can actually do what I'm going to show you across 8 kilobytes of data. If you actually replicate what I'm going to do across thousands of subarrays, you can potentially do this on 8 million bits concurrently in a cycle. Okay, let's activate these 3 rows. If you concurrently activate rows A, B, C, basically these capacitors get connected to their word lines and bit lines, sorry. And essentially what you get is if at least 2 of these cells are charged in an ideal circuit, if at least 2 of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state at the end. And that's a bitwise majority function. Basically, you can get the bitwise majority in real DRAM chips. And again, later work, we showed this in circuit simulations in our paper, in this 2015 paper. Later work showed that by violating the DRAM timing parameters, in some DRAM chips, you actually can get this bitwise majority function. We have some work ongoing that has replicated that work, and that's absolutely true. You can actually get bitwise majority function by activating multiple rows in DRAM, just like we have shown, except you can do this in real DRAM devices by violating the timing parameters such that you kind of get the triple row activation effect. Okay, so a bitwise majority is very interesting, but if you actually set C to 1, you get the OR of A and B. If you set C to 0, you get the AND of A and B. So that's nice. We get AND or bitwise majority. What about NOT? How do we functionally complete? Well, NOT actually exists over here. Whenever you activate 1 row in DRAM, the complement is actually on the other side of the bitline sense amplifier. So in this in the micro paper, we propose that you connect this to another row such that you can actually get the complement of a row. So basically, you can be functionally complete. And once you're functionally complete, if you're actually careful about how you design your algorithm, you can redesign your algorithm to basically take advantage of these bulk bitwise operations. You can implement anything on the substrate. And we've actually been showing that. I'm going to show you a later work. But some algorithms are actually much more amenable. For example, databases use bitmap indices. They do a lot of bitwise and, or, XOR, etc. And people actually design databases to maximize these bitwise operations. And people design web search engines to actually maximize the bitwise operations. And there are many other applications that are using bulk bitwise operations today. We ported the bitweaving database to our simulator that simulates Ambit. And we see significant performance improvements, energy efficiency improvements on end-to-end query execution using the substrate. So you can see that the results are actually quite promising. And if you're interested, you can read the paper. And the later papers, like the compute DRAM paper, showed that you can violate the DRAM timing parameters. And on some DRAM chips, you actually get the majority function, AND function, and OR function. Okay, so how do you make this programmable? So the problem is this is not easily programmable, at least from the get-go. You need to redesign your algorithm. So we're tackling the programmability issue right now. And this is a paper that was published in ASPLOS, but we have some papers coming up as well. So it turns out you can actually express any of your desired operations using AND or NOT logic as a programmer. This could be convolution. This could be matrix multiplication. It could be your favorite operation. It could be any abstraction level also. We convert this to a majority NOT logic. This is called a majority inverter graph. We optimize this majority inverter graph using some quantum computing compiler, actually, that was developed by EPFL, Nani de Michele's group. And we translate that majority inverter graph to a microprogram that is associated with this desired operation, which could be a convolution, for example. And this microprogram gets stores in main memory, and the memory controller invokes it whenever necessary. So you basically associate an instruction, a new instruction, with a microprogram that consists of DRAM commands. DRAM commands are triple row activation, pre-charge, row clone, for example, and some other things that are essentially standard DRAM commands. Now, if this desired operation is called from an application, it gets translated by the processor to be executed in the memory controller, and the memory controller executes it according to the microprogram that we stored. So that's the idea. And with this, you can actually execute anything, if you will. We evaluate this across 16 complex operations and 7 real-world applications, and we see the significant performance as well as energy efficiency improvements compared to both a high-end CPU as well as high-end GPU. And you can read the paper for more detail. We don't have time to cover it, but there's more work to be done in this area to enable programmability. People are developing compilers for this sort of bit serial processing. There have been compilers, for example, at the HPCA conference this year, as well as, I believe, PPOP or CC, don't quote me on one of those conferences that were concurrent with HPCA. So people are actually developing compilers to this end. We need to do more, of course. So some operations are difficult to execute this way. So we actually add lookup table-based execution support to the DRAM, so that we can do much more sophisticated operations in DRAM. And you can take a look at that if you're interested. And a lot of the source code is open source. You can actually find out. You can also implement security functions in DRAM. These are examples of processing using memory. We've shown that by violating some timing parameters, whenever you access DRAM, if you violate the timing parameters, some cells fail very reliably to form the signature of the device. These are based on real DRAM chips across many workloads. Across many DRAM chips. And this can be used for remote attestation, for example, as a physical unclonable function. Similarly, if you violate the timing parameters, some cells fail randomly, meaning they're actually a random number generator. So you can identify these random number generator cells, and you can actually supply random numbers to the program on the DRAM side. This is useful because if you're doing in-memory computation, it makes sense to have security support, random number generation, PUF support, etc., on the DRAM side. And we've been looking at random number generation. And these are, again, backed up by real results from real DRAM devices. All of these are real DRAM device studies. We actually find new ways of doing that at higher throughput in this paper. And then you need to have end-to-end design and system design to actually take advantage of this. In our PyDRAM work that I mentioned earlier, you can download it, you can put it on your FPGA, and it can actually generate random numbers that you can use in your real programs. And we'd be happy to support it. Okay, I mentioned that I'm going to talk about some other technologies that are common as well. You can do similar things in Flash, essentially. I'll give you the basic ideas relatively quickly over here because we don't have a whole lot of time to cover everything. But in this micro paper, we've shown that you can reliably perform bulk bitwise operations in NAND flash memory, in real NAND flash chips. So let me summarize this. This is actually, you can actually do multi-operand activation, which enables bulk bitwise operations with a single sensing operation inside the flash device at high reliability. And this improves performance significantly compared to traditional systems, as well as prior systems that use flash. And this is low cost, and it requires no changes to the flash cell arrays. So let me give you the basic idea. Essentially, you may have operands on many pages, let's say 32 pages in DRAM. Oh, sorry, not in DRAM, flash. These are flash pages. Basically, by activating 32 rows concurrently, you can get the end, bitwise end, in one simultaneous sensing operation. This increases the latency a little bit, but our experimental results show that it's no more than 10%. And we improve the accuracy by playing tricks in the flash controller, which I'm not going to talk about. So basically, the key idea is very simple. If you simultaneously activate multiple word lines in the same flash block, because of the resistance characteristics of the flash operation, you get the bitwise end of the stored data in the word lines. And we can do this up to 48 operands. Now, if the word lines happen to be in different blocks in the flash memory, and if you simultaneously activate them, you get the bitwise OR of the stored data in the word lines. And we can do this across 4 operands because this is across multiple blocks and it's a heavy operation. So basically, we can get bitwise OR and bitwise AND. Now, bitwise NOT is free in flash because you have the inverse read operation that already exists in the flash controllers. So you can also do NAND, NOR, XOR, and XNOR, and you can read the paper for more detail if you're interested in this. So for this, we also did a lot of real device characterization studies across many, let's say, hours and months, actually. Basically, we showed that both intra and inter-block multi-word line sensing operations require no changes to the cell array. And you can actually activate multiple word lines up to 48 for bitwise AND, up to 4 bitwise OR, with small increasing sentence latency. And our mechanisms for improving reliability, significantly improve reliability, and we observe no bit errors in the tested flash cells. And I'd invite you to read the paper for more detail. We don't have a lot of time, but I think this is actually important because there will be a lot of workloads that do not fit in main memory, and I believe we need to do a lot more processing on the storage size going into the future. Now, you can do similar things in non-volatile memories. This paper shows that you can actually activate multiple rows in non-volatile memories, and you get row copy operations as well as bitwise operations. I will not talk about this in detail. And as earlier tutorials, I believe, showed, you can do crossbar array operations in emerging non-volatile memory technologies that have this structure so that you can do matrix vector multiplication in the analog domain. I believe this is fascinating also. This you cannot do in DRAM or flash, in my opinion. You have to reorganize the array significantly to be able to do that. And even if you do that, it's going to be very difficult. But basically here, you can perform dot product operations using crossbar arrays. And the fundamental principle is you use Kirchhoff's laws. And the idea is that bit line current is a sum of products of the word line voltage times the cell conductance that's stored in the cell. I think this requires a lot more analysis for reliability, etc. Let me give you the basic idea. Basically, this is mainly used for matrix vector multiplication today. You have a matrix. Matrix is stored inside this non-volatile memory array, if you will. It could be memristors, it could be RRAM. Basically, you encode the matrix values as conductances, which is 1 over resistances over here, inside this crossbar entry, if you will. And we input the voltages, we input the vector that we're going to multiply the matrix with as voltages on the word lines. And when you apply the voltages on the bit line current is really the sum of the voltage here multiplied by the conductance and the voltage here multiplied by the conductance. Essentially, that's what you get. And this is very useful, clearly, and people have demonstrated this on real non-volatile memory chips that I'm not going to talk about in detail. But you can actually find a lot of information over here, and there are a lot of papers that are being written at ISSCC, CICC that talks about this. I think this is fascinating. This is also somewhat longer term because processing using non-volatile memory is also longer term, in my opinion. There are some other challenges to be resolved. And people are actually adding processing near memory to enable this, as we're going to discuss next. Okay, so that concludes the processing using memory part of this lecture. Now, in the remaining time, about, I think, 15 minutes, so that we can actually accommodate time for questions in the end. I'm going to talk about processing near memory, which I believe is shorter term. It's already happening. And this is the idea of putting logic closer and closer and closer to memory. Now, the definition of what is closed depends on what you want to do, essentially. It could be inside the subarrays. It could be very destructive to the subarrays, but maybe we don't want to actually destroy the density of the DRAM chips as well. So the closest parts is actually near the subarrays or near banks, but processing inside the DRAM chip is a form of processing near memory if you put logic there. Okay, the mindset is going to be still the same. We're going to treat memory as an accelerator over here, and we're going to put some compute capability. It could be general purpose. In fact, I'm going to start with specialized motivation, but we can actually put a lot of general purpose compute capability here as well. And when we first started looking at this, we basically looked at different applications, and we were very interested in graph analytics, because graph analytics is a very challenging problem, and we have increasingly larger graphs in our systems. And this is very memory bound. Our graphs are increasing, and our unfortunately, memory processing capability is not increasing on the memory side, because we have frequent random memory accesses and little amount of computation to cover for it. This is a very good application to put on the memory side. And later, we have actually more works in this area that look at graph pattern mining. I might mention that if we have time at the end. So at the time, we were actually very interested in 3D stacked memory. 3D stacked memory is a good substrate where you can do near memory computation, because you have a logic layer underneath memory layers. And the logic layer is connected at very high bandwidth, low latency, and reasonably low energy to these memory layers. And you can actually put a lot of logic over here. And other true three-dimensional technologies are under development, clearly. There's monolithic three-dimensional technologies, and also there are carbon nanotubes. You can actually put memory and logic interleaved in a much denser way going into the future. And this is a prime place to do processing near memory. And we wanted to do that. We wanted to take a look at that. We're going to treat this as an accelerator. We basically have a host processor. We offload graph computation to a distributed system of these 3D stacked cubes, if you will. So we have one cube, we connect them together to many cubes, and we offload the graph computation on top of this. The programmer, it's kind of like a GPU, primitive GPU. Old GPUs used to be this way. It's kind of like that still, but you can offload basically graph computation. And the programmer does the mapping of the graph nodes to the cubes, as well as graph nodes to these vaults. And if you look at the logic layer, inside the logic layer, it's partitioned. Each partition has an in-order coordinate, as well as a memory controller. Basically, we add the in-order core, simple in-order core. So you can actually do general purpose processing. And the in-order code actually accesses the memory on top of it, on top of the stack. Now, in order to minimize the data movement, we do not move data as much to the functions. We actually move functions to the data. So this is remote procedure call-based programming. Whenever we want to update a graph node, the processor that wants to update the graph node sends a message to the processor that houses that graph node on top of it, so that the update is done in place without moving the data that's updated. And that's the idea. This is very similar to the remote procedure call-based programming models that's used in data centers today. So it's not that difficult, but of course, it's a bit difficult in the microscale, because microscale systems are not programmed this way currently. And we have a lot of prefetching mechanisms to exploit the high amounts of memory bandwidth that's available to the logic layer. Okay, I can go into a lot more detail, but unfortunately, there's a lot of detail over here. The paper is a full system design. And you can take a look at the paper. And basically, we compared to state-of-the-art system at the time. This is around 2013 or so. You can see that all of these state-of-the-art systems is very different from what we call Tesseract. Tesseract doesn't have the compute-memory dichotomy. Memory and compute are together, and you have a distributed system of memory and compute units. And as a result, you expose huge amounts of memory bandwidth at the time to the cores. And as a result of the memory bandwidth, as well as the processing near memory capability enabled by the programming model, we get significant performance improvements. So you can see that we get close to 14x performance improvement averaged across 5 graph processing algorithms. And this is work at the time. Later work actually did a lot of things at the system level, as well as the specialize the logic more to the graph processing. And today we're close to 100x. Basically, we can improve the graph processing performance by 2 orders of magnitude. We showed that you get significant energy reduction because we reduced data movement significantly. Later works actually improved on this number. Today, we're actually close to 100x as well. So basically, we can get 2 orders of magnitude improvement in terms of performance, as well as energy at the same time. And this is using 3D stacked memory technology in an intelligent way by changing the programming model, etc. And if you're interested, there's a lot more detail in the paper. But this is an example of rethinking the entire system design for acceleration of an important application. But we can actually do simpler things. And I'm going to talk about what we can do in the storage side relatively simply without completely changing how we design the application. And I'm going to talk about genomic data filtering. This is more recent work that we published last year. And if you look at genome sequence analysis, today there's a lot of data movement. You move a lot of data from the storage system to the main memory, to the caches, to the computation unit. And this has a lot of computation overhead as well as data movement overhead. Today's systems actually use a lot of heuristics, accelerators, filters on the main memory, cache, and computation side. This reduces the computation overhead and some of the data movement overhead internally to the right-hand side over here. But the data movement overhead from the storage remains, which is actually a huge bottleneck. In fact, this exacerbates the data movement overhead from the storage because as you improve processing on the right side over here, the data movement overhead becomes a larger bottleneck in terms of energy and performance. So the idea we have over here is specialize the storage system slightly such that you can do filtering operations in the storage device. This is an NAND flash SSD in this particular case, such that you move very little amount of data, genomic data, to the computation units. Now, I'm not going to talk about exactly how we do this, but there are different things you can take advantage of. If something exactly matches a reference genome, for example, you don't need to move it. You can detect it very quickly in the storage system. If something is definitely not going to match the reference genome, you can also detect it relatively quickly in the storage system. And that's the idea. Now, if you do that, you can actually reduce the data moment overhead significantly. And our results show that you can get more than 30x performance improvement, as well as close to 30x energy reduction in genomic applications. And again, this is not a trade-off. You improve both performance and energy at the same time by doing near storage processing in the flash controller. Okay, if you're interested, you can read more about it. So these are relatively simple approaches. We actually offload functions to memory. And we've actually been looking at doing that on the DRAM system as well. I've already given you some idea about this paper that we did with Google a few years ago. Basically, we identified a bunch of important applications that look like this. You can see them here. And we found out that most of the data movement that is responsible for most of the system energy is coming from simple functions. And we actually can design lightweight logic to implement these simple functions in the memory side. You can have a small embedded low power core to implement these functions, or you can have small fixed function accelerators, or you can have FPGAs. In this particular paper, we did not explore FPGAs, but I believe they're really important. And we show that by doing this sort of function offloading, not rewriting the entire application, but identifying functions and offloading them to the memory side accelerators, you can get significant performance improvements like 2x, more than 2x, let's say. So what are some of these functions? You can read the paper for more detail. But for example, in machine learning inference that's used in edge devices, more than 50% of the inference energy is spent on data movement, and more than 54% of that is coming from two simple functions: packing and unpacking of data and quantization of data. And these are actually relatively simple computationally, so you can offload it to very simple logic on the memory side. And that's what we did, and we get significant performance energy improvements. And I'll refer you to the paper for more detail. So, okay, I can give you a lot more examples, but we don't have a whole lot of time, so I'm going to skip over some of these examples. You can actually do a lot of interesting things: accelerate linked data structures, accelerate prefetching mechanisms, accelerate climate modeling, approximate string matching, sequence to graph mapping, and a lot of genomic analyses. Time series analysis, which is used in many domains. You can accelerate these with 3D stacked memory, and graph pattern mining, another example of graph analytics. In this particular paper, we actually developed an end-to-end system design algorithms, as well as set-centric formulation of these algorithms, and the set-centric instruction set architecture that can be used very nicely with processing using memory, as well as processing near memory systems. If you're interested, this is really across the stack design, all the way from algorithms. It changes the ISA as well, and also the underlying processing near memory and using memory systems. So there's a lot more examples in database systems, neural network inference. I'm going to talk about this neural networks inference a little bit because this is kind of interesting and people are interested in it. And then we're going to look at some real world PIM systems. Let me give you quickly what else did we do with Google. Basically, after we looked at their real workloads, more general purpose, we also wanted to look at these neural networks that are used in Google Edge TPU as Edge ML accelerators. And we looked at 24 proprietary Google Edge models, and we found out that basically the Edge TPU is very much bottlenecked by memory. And the reason is it's very monolithic. It's very compute-centric. It doesn't take into account the characteristics of different layers that you execute in neural networks. And we propose a more heterogeneous acceleration framework that has a compute-centric accelerator as well as 2 data-centric accelerators. And in the end, across all of these edge models, we can improve performance and energy by more than 3x, as you can see. It can also have a simpler area cost. The combined area cost of these 3 accelerators is smaller than the area cost of the existing Google Edge TPU, because existing Google Edge TPU is actually quite over-provisioned at the time. So we analyze a bunch of neural network models and we look at their characteristics, and there's a huge diversity in their characteristics in terms of their memory characteristics as well as computation intensity characteristics, as you can see. And there's a huge variation inside the same model across different layers, for example. And you can see the huge variation. There are orders of magnitude differences in terms of both memory characteristics as well as computation intensity characteristics. So basically, we questioned whether or not it makes sense to have a monolithic accelerator that tries to cater for all of these different characteristics. And it doesn't work that way. So basically, we design a heterogeneous acceleration framework where you divide the accelerators such that they can cater for different types of families of neural network models and layers. And 2 of these accelerators have to be data-centric because there's a huge data-intensive part of these neural networks, as you can see. If you really want to know about the design of these accelerators, the paper covers all of them. You can find them online. But you need to identify the layer family. So you need to actually have some software support to identify the different layer families such that you can schedule them on the appropriate accelerator. And you can see that there's a significant amount of energy reduction you can gain. The Mensa bars, average Mensa bar, it's more than 3x actually. But you can see that some workloads, these are actually the heavy neural network models, long short-term memories and transducers. In the baseline and also baseline with high bandwidth memory, they're very much off-chip interconnect and memory bound. So if your model is huge, you're very much memory bound, even if you have an accelerator. And we actually reduced that bottleneck significantly by pushing the computation to the memory side by using 2 data-centric accelerators. And you can look at the throughput and latency improvements in the paper. We don't have time to cover that. Okay. So I also mentioned the FPGA-based processing near memory mechanisms you can do today. I'm not going to mention them again, but you can see some examples. These are examples of different cases where we revisit the entire stack. We're doing algorithm, architecture, logic, co-design in many of these cases. But in some of these cases, it's relatively simple. In some of these cases, it's very disruptive. Now, the paper that I mentioned covers a lot more. I don't have time to talk about it. We actually have another paper that talks about the programming ease challenges in the IBM Journal of Research and Development. Now, in the remaining time, let me quickly talk about some adoption challenges. So you can design any hardware in the end. The question is whether it will be adopted. So I think adoption issues are really important. And these are mostly about the stack on top of the hardware, meaning application of software, programming, system and security support, runtime and compilation systems to take advantage of it, ease the programming, and infrastructures to assess benefits and feasibility. I believe we need to do a whole lot of work in this area, combined together with the circuit level and device level work to enable in-memory computation. But I believe all can be solved with a change of mindset. Unfortunately, the processor-centric mindset dominates our entire stack. We need to change that mindset to a data-centric mindset. So I believe we can get there step by step. That's why accelerating key applications is important. So I'm going to skip a lot of these because I already covered a lot of these. That's why we basically covered some of these applications. But we also need to think about how to keep it simple. So simplicity is important. And I did not talk about it as much, but using simple instructions to execute in memory is actually a simple way of enabling adoption. We need to think about coherence mechanisms because current coherence mechanisms don't work well for near memory processing. We need to think about synchronization, virtual memory mechanism, and there's a lot more to do over here. Now, let me quickly talk about hope, meaning some things are happening in the real world. And I've kind of mentioned this, but let me go into a little bit more detail. If you're interested, you can we actually do a lot of tutorials and architecture and systems conferences on real processing in memory systems. You can find these online. Most recent one was at ASPLOS. And if you're interested, we have one coming up at ISCA in June that talks about these. And we have invited talks from companies that do actually processing in memory. I will mention the UpMem processing in DRAM engine. Here, the UpMem company developed real DRAM chips. These are real DRAM chips modified to actually have processors. And we actually do a lot of studies with these systems. And this is what the processor looks like. Next to each bank in DRAM, you have a sophisticated general purpose simultaneous multi-threading processor. Now, it doesn't have a whole lot of computation capability, like the multiply instructions are limited. There's no floating point computation support, but some applications benefit a lot. And if you're interested, you can read our papers, watch our talks, etc. And Juan, who is a senior researcher in my group, has been giving a lot of tutorials on this. Again, I don't have time to go over this, but this architecture benefits from applications, it benefits applications that are very memory bound. If you're doing heavy computation, this architecture is not a good fit. But if you're very much memory bound, there are some applications that would benefit a lot. You can outperform existing CPUs and GPUs significantly. Some workloads, not so much. You need to basically program this architecture appropriately. Okay, so I'm not going to talk about this, but I will mention that there are workloads that we have released. You can actually incorporate them in your system or actually decide to contribute to these workloads. And they're all online open source. Okay. So we recently actually looked at machine learning training on the system. This is the work that's going to be presented at the ISPAS conference tomorrow, which I'm also not going to be able to attend. But basically, Juan is going to present this. If you want to do machine learning training on this real system, you need to optimize things. You need to optimize the data representation. You need to optimize things to do lookup table-based computation. And you need to optimize data placement and layout for streaming. And if you do that, you can then outperform the CPUs and GPUs. So it requires work, basically, even with this near memory processing engine. And if you're interested, you can find it in our paper that's already written, as well as talks online. Okay, I'm going to skip this because we actually have been looking at sparse matrix vector multiplication quite a bit, and we release libraries. If people are interested, again, they can do it on real processing in memory systems. But I will mention that this is a very tough workload for the UpMem system. So UpMem is not the only company. As I mentioned, Samsung has been developing DRAM chips. These are real DRAM chips modified to actually do processing in memory, near memory, next to each bank in this particular case. In this case, specialized for machine learning. They added floating point support for multiply and accumulate. And this was presented at ISSCC a couple of years ago. And you can see that it's next to each bank, and there's an ISA for it. And they actually, I have not worked with these chips, but they actually have been working with people to write papers to show benefits. Samsung and Facebook modified a DRAM board to actually have recommendation inference acceleration in this buffer chip. Clearly, you can add a lot more logic to this buffer chip over here, and they also write papers. And as I mentioned earlier, SK Hynix as well modified a GDDR6 chip, a DRAM chip, and they reported their results in ISSCC last year for machine learning again. And if you're interested, they actually talked about this in our Ask Plus real world PIM tutorial. You can find this information online as well. And I've also mentioned these are actually all DRAM chips, real DRAM chips. Alibaba also has designed their DRAM chip to do recommendation inference for kind of similar purposes, but their design is different from the other designs. So basically, this is happening in the real world, but we need to do a whole lot more to enable the adoption barriers. We need to keep the real chips coming, but we also need to make sure that the software stack on top of those real chips is built. So some of the software stack needs to figure out which workloads can benefit and which functions can benefit. And we actually do a lot of work on identifying different applications. In this work, we analyzed more than 300 applications and figured out which functions in these applications can benefit from near memory processing. And this work developed a methodology to identify memory bottlenecks. I will not go into detail. I'll let you read the paper. But this sort of methodologies need to be automated going into the future so that we can automatically take an application and translate it to a particular processing in memory system. That's why we open source a lot of our work, and you can find them online. And you can find the papers online also. Okay, so I'm coming to the end. Basically, we have a huge challenge and opportunity for the future. We want fundamentally energy efficient architectures. And I think that requires us to be data-centric, doing processing close to memory. We want fundamentally high performance architectures. I think that also requires us to be data-centric. So I think we have nowhere to escape. So we need to minimize the data movement in our systems. So there's more tutorials that we have. If you're interested on the slides that I've skipped and the other slides, you can actually look at them. Let me conclude. I think we're at a point where we really must rethink how our systems are designed today. Today, we have a gross imbalance in our systems. Only computing devices can actually do computation. Memory and storage and communication device cannot do computation. And in order to be high performance and energy efficient, we need to be more data-centric. I did not talk about in this talk, but we also need to be data-driven and data-aware. We need to enable computation capability inside and close to memory, storage, sensing structures, everywhere, essentially, where data is or where data is generated. Hopefully, I've shown you that this can lead to orders of magnitude improvements. And I believe, actually, these orders of magnitude improvements can increase. I believe this can enable new applications and computing platforms, especially if you focus on mobile and portable devices that can do, for example, genome sequence analysis, but there's a lot more over there. I believe this can also enable a better understanding of nature, because nature is actually fundamentally a lot more data-centric and data-driven and data-aware as well. So who knows what else? So I believe the future of truly memory-centric computing is bright, but we really need to do the hard work to enable it. Okay, I think I'm at the end. So I believe we need to revisit the entire stack for this. Any questions? So I should really actually acknowledge the funders of this work. More than anything else, I will acknowledge my group, and I will leave you with this picture. But we actually do a lot of artifacts online, so you can find that online. So I'm going to conclude here. Let me. I'm happy to have any questions.
Thank you for the passionate presentation. And the session is open for the question. Any question? Yeah, hello, thank you. Too bad we can't see each other, but hopefully you can hear me.
I can hear you.
I'm curious if you could perhaps, given your deep expertise and interaction with a lot of users, you've mentioned the weather modeling, the genomics, graph analytics, and so on. What's your outlook on some of the success stories for the adoption, right? Because these are, as you've pointed out, very difficult technologies to take advantage of. And so if we're going to, convince the users to move from their processor-centric world to the data-centric world, our instruction sets that we throw at them are completely different. They have to adapt. And like you said, we need to make the tools there to enable them. We can push chips at them all day. You put a lot of good examples, Samsung, Alibaba, SK Hynix. There's all these chips being pushed out, but I'm not seeing the pull. But I wonder, of course, I go to a lot more circuits and architecture conference, so I mostly see the chips. What I'd love to get your perspective on is, are there success stories where we can see this technology being pulled up and embraced and utilized by the users who want to, plug these into their genomic sequencing tools, for example? What is your outlook on where the success stories have been so far, and how can we, increase the number of these success stories going forward?
Yeah, thank you. That's a great question. Unfortunately, I'm not going to be able to give you exact success stories. There's a lot of interest in the user space in the processing and memory technology, and there are some users who are trying. And as far as I know, there are no, let's say, public success stories, because we're still new to this, I would say. If you look at all of these chips, they're from 2021, 22, UpMem is 2019. So I believe we really need to be doing these application level studies, and users definitely show interest, but adoption will take some time. Why is that? So if you look at, I actually think of a lot of the history of this is going to be somewhat similar to GPUs. If you look at GPUs were compute devices embedded into our systems starting from 1990s. And some folks, some really interested and experienced and expert folks said, can we use this for computation? And they actually did a lot of hard work to get their applications running on GPUs. Even then, it took, let's say, NVIDIA for a good amount of time to turn this into a programming model that could be exploitable or exploited by a large fraction of users. I don't think we're there yet. I think we're kind of at where we are with GPUs. We have this hardware coming up, and enthusiasts are trying to figure out, what can we do with this? What can we accelerate it? So the programming models are not developed yet, but we do need to develop them. We do need to figure out what is the right programming model to enable a lot of these. What is the compiler support? I believe NVIDIA did a great job to exploit the hardware that existed there in GPUs. So that's my best answer that I can give you at this point. I don't believe the success stories are going to be immediate. If they are, then people are going to take advantage of them, perhaps without talking a whole lot about it. Maybe they're taking advantage of them. I'm not sure. But the general purpose success will come once something like what happened to GPUs happens to this sort of systems.
Maybe it's somebody in the stock market.
Potentially, yeah. I don't know.
question? Okay, I think time is almost done. So I think time is almost over. So I would like to close the presentation and let's thank the speaker.
Okay, thank you very much.
I think we will have a 15-minute break and then we will start the next